Chapter 1.6 is other types of equations and applications. Be aware this section has 4 different kinds of equations in it that we're going to talk about. So there's a lot of information in this section. The first kind of equations that we're going to talk about are rational equations. Do you remember what the word rational means? Rational numbers are fractional numbers, right? So rational equations are equations with variables in the denominator. Remember, just because an equation has a fraction in it doesn't make it a rational equation. This is just a linear equation. We look at what's being done to the x. The placement of the x determines the type of equation. So just having a fraction in your equation does not make it a rational equation. When your variable is in the denominator, then you have a rational equation. However, it's just like a fractional equation, an equation with fractions in it. Anytime I have an equation, I'm getting rid of those fractions. For example, with this one, I would get the least common denominator, which is 4, multiply everything by that denominator so that I would get rid of the fractions and wind up with a simple linear equation that we can then solve. So the same thing over here. The difference may be, it may not be as easy to determine what our common denominator is. So our first step in finding the common denominator is to factor all the denominators. This one doesn't factor any further, doesn't factor. X squared minus 4 is the difference of squares. So it will factor as x plus 2 times x minus 2. So I'm just going to rewrite that denominator as x plus 2 times x minus 2. Now, to find the common denominator, once we see all our factors, I take all the factors that any of them have in common. So some of them have an x minus 2. Some of them have an x plus 2. And then any extras, right? And there are no extra factors. So this is my common denominator. This doesn't have anything extra that I don't already have included. This doesn't have anything extra that's not already in my denominator, nor does this. So that's my common denominator. Once I find my common denominator, I simply multiply every term by that common denominator. So I'm going to multiply everything all the way across by x plus 2 times x minus 2. X plus 2 times x minus 2. X plus 2 times x minus 2. And then anything that's the same on top and bottom, any common factors in a fraction can divide out. So the first term becomes simply 3 times x plus 2. And then plus the next term, I can divide out the x plus 2's, so it's just 1 times x minus 2. And on that last term, the entire x plus 2, x minus 2 can divide out, which will just leave the 12. So now here's the equation I need to solve, and it doesn't have any fractions in it. So first step, distribute and get rid of those parentheses. 3x plus 6 plus x minus 2 equals 12. It's just a linear equation, so I'm just going to combine my like terms here. 3x plus x is 4x. 6 minus 2 is a positive 4. Because it's linear, I'm just going to move all the constants to the other side of the equation to get that x term all by itself. And then divide by 4. X equals 2. Okay, one difference in rational equations and equations that just have fractions in it is also we must check our answers. I don't have to plug it into the whole equation and see if it's equal. I have to make sure that when I plug it in, it doesn't make a denominator 0. Remember, denominators cannot be 0. Denominators cannot be 0. You cannot divide by 0. Over here, I don't have that problem. I would never write a fractional number with a denominator of 0. But here, notice, if I let x be 2, and I plug it in right here, 2 minus 2 is 0, telling me, wait, that's not a valid answer. Do not leave x equals 2 anywhere on your paper. You've got to mark it out saying, I realize that's not a valid answer. And so that means there must be no solution to this equation. So don't forget, we must check our answers. In this course, there are going to be 3 times we have to check our answers. Here's the first one, rational equations, because denominators cannot be 0. So anytime you have a rational equation, don't forget to check your answer. All right, let's try that again. All right, here's another rational equation. Pay attention to what kind of equation it is because that determines the method we use to solve it. With a rational equation, just like any other equation with fractions in it, I'm going to get rid of those denominators. To get rid of the denominator, I need to see all the factors. That doesn't factor, but here I can factor out an x. So I'm going to replace this with x times x minus 2. Now, some of them have an x, some of the denominators have an x minus 2, and there are no extra factors. There's nothing extra here over what I have written here, or here, or here. So that's my common denominator. That means I'm going to multiply every one of these terms by that denominator all the way across, times x minus 2, times x minus 2. Now in this first term, the x minus 2's get to divide out, which just leaves x times 2x plus 1. Okay, in the second term, the x gets to divide out, which just leaves 3 times x minus 2. And again, in the last term, the x and the x minus 2 get to divide out, which just leaves the negative 6. Again, I now have an equation without denominators. So getting rid of the parentheses, I have 2x squared plus x plus 3x minus 6 equals negative 6. This time I'm left with a quadratic equation. So with a quadratic equation, I'm going to first of all try to factor it, since I notice I can't use the square root method. If I'm going to try to factor it, I want it set equal to 0. So I'm going to rewrite it, combine my terms, and add 6 to both sides so that it equals 0. However, there's a 0 there also. So I wind up with 2x squared plus 4x equals 0. And to factor that, I just factor a 2x out of both terms, leaving an x plus 2, meaning 2 equals 0, right? X equals 0, or x plus 2 equals 0, using my zero product property. Well, 2 is not the one that's 0. But here's x equals 0, and solving this, I get or x equals negative 2. But don't forget, because it's a rational equation, I have to check each one of these in the denominator. 0 minus 2 is fine. It's not 0. I don't care what it is, as long as it's not 0. Oh, but that would make a denominator with just a 0 in it, so that also isn't my solution. Let's try negative 2. Negative 2 minus 2 is not 0. Okay, negative 2 is not 0. Negative 2 times negative 4 is not 0. So x equals negative 2 is my solution for this equation. Okay, factor all the denominators. So this one factors two numbers that multiply to give negative 2 and add to give positive 1 are positive 2 and negative 1. This one is the difference of squares. So x plus 1, x minus 1. And this one I can factor out a 2 right off the bat to start with. And then continue factoring. I need two numbers that multiply to give 2 and add to give 3. So that's x plus 2 times x plus 1. Now to find my common denominator, I take whatever they have in common. Some of them have an x plus 2. Some of them have an x minus 1. Some of them have an x plus 1. And then this one has an extra 2. Take what they have in common and everything extra, right? This doesn't have anything that's not listed down here. This doesn't have anything that's not listed. This doesn't have anything that's not listed. So this is my common denominator. That's what I'm going to multiply every term by. Times 2 times x plus 2 times x minus 1 times x plus 1 times 2 times x plus 2 times x plus 1 times x minus 1 times 2 times x plus 2 times x plus 1 times x minus 1. Okay, on this first term, the x plus 2 and x minus 1 can divide out, which leaves us a 6 times x plus 1. Okay, then I have a minus. So here, the x plus 1 and x minus 1 both get to divide out, which leaves a 2 times x plus 2 equals, here, the 2 and the x plus 2, x plus 1 get to divide out, which leaves 7 times x minus 1. Okay, so distributing, 6x plus 6 minus 2x minus 4 equals 7x minus 7. So even though this was a nasty, nasty looking equation, in reality, all I have to do is solve a simple linear equation. So I'm going to combine my like terms. 6x minus 2x is 4x. 6 minus 4 is positive 2. Okay, put all my variables on the same side. So subtract 7x and subtract 2, constants on the other side. Given 4x minus 7x, can't hardly read my writing on here sometimes, is negative 3x equals negative 7 minus 2, negative 9. Divide by negative 3 for a final answer of x equals 3. But don't forget, with rational equations, I have to check and make sure it doesn't make a denominator 0. 3 plus 2 is not 0. 3 minus 1 is not 0. 3 plus 1 not 0. 3 minus 1 not 0. 3 plus 2 not 0. 3 plus 1 not 0. So x equals 3. It's a valid answer. Okay, the next kinds of equations are radical equations. So to be a radical equation, it means you've got a variable underneath the radical sign. Again, if you have an equation like this, not a radical equation, right? To be a radical equation, the variable has to be in the radical. Your goal is to get rid of that radical sign, just like your goal on solving any equation, right? If it's a linear equation, you're just undoing all the operations to get the x all by itself. Same thing here. This is one of the operations you want to undo, is that square root. We just have to be careful. A couple of things, they're really the same thing, but a couple of things we have to be careful of are these first two steps. All right, let's do an equation that we can easily tell the answer to. 2 plus 3 equals 5. Okay, if I go through here and square my individual terms, I get 4 plus 9 equals 25, which is not true. It's not true. That does not work. We cannot square individual terms. However, if I squared both sides of that equation, right, then do an inside parentheses first, I'd have 5 squared equals 25. Oh, yes. So first thing, we cannot square individual terms, only sides of the equation. Okay, so second thing, which is for the same reason, we have to isolate one of the variables or it's not going away because I can't square individual terms. Think about this. If I had x plus 2 and I squared it, that is not x squared plus 4, right? That's x squared plus 4x plus 4. Okay, so we can't have anything over with the radical or it won't go away. It'll just create more radicals. So first of all, isolate one of the radical signs. We only have one here. So I could subtract my x and then get rid of the negative, but I could do that all in one step if I just move this to the other side. So isolate a radical on one side of the equal sign. In other words, get it all by itself. So that's a big fat 0. And I have x equals the square root of 3x plus 18. Then I'm going to square both sides, not individual terms. Here I only have one term on each side, so it doesn't really come into play. But remember, both sides, not individual terms. Because when you square a square root, they undo each other. So I'm left over here with the x squared, but over here with just 3x plus 18. Now it's no longer a radical equation, it's a quadratic equation. So I'm going to set it equal to 0 and try to factor it. Two numbers that multiply to give negative 18 and add to give negative 3 are negative 6 and positive 3. So therefore, x equals 6 or x equals negative 3. This is the second time, so 2 of our 3 times we're covering today of when you have to check your answer. And in radicals, I've got to check both of these answers in my original equation. Because of the way that we square both sides of the equation, we introduce what could be called extraneous solutions or extra answers. There'll be a solution to this equation, but they may not necessarily be a solution to this equation because of when I square both sides, it takes out the difference between positive and negative, right? So keep this in mind. We never say if there's a radical in the equation at the onset, right? If the equation starts out with a radical, that radical is assumed to be the principal root, only positive. If I put the radical in the middle of an equation as I'm solving it, right, then I have to say, oh, that could have been plus or minus. But if it started out in the equation, like this one, that is 2. I do not say that's plus or minus 2. So when I'm checking these, I got to keep that in mind. Let's plug each one in to the original equation. Let's let x be 6. So 6 minus the square root of 3 times 6 is 18 plus 18. And I want to know, does that equal 0? Is 6 minus the square root of 36 equals 0? Square root of 36 is 6. 6 minus 6 is 0. Yes. So there's one answer. Now, they might both be answers. Neither could be an answer, or just one could be an answer. So I must check both of them in the original equation. Let's try -3. Is -3 minus the square root of 3 times -3 is -9 plus 18. Is that equal 0? So is -3 minus the square root of 9 equal to 0? Is -3 minus 3 equals 0? No. So make sure you mark that one out. All right, let's try that again. Isolate one of the radicals. This one only has one radical, so I'm going to isolate the radical. I would have square root of 4x plus 5 equals 2x minus 5, right? And then square both sides. Not individual terms, both sides, right? This is not 4x squared plus 25. A square and a square root undo each other. So I have 4x plus 5 equals, now I could write this out, but some of these problems get plenty long enough, and so any work I can save is beneficial. Hopefully, we're learning that shortcut for multiplying this out if we don't already know it. Square the first one, multiply everything together, so that's -10x, and double it, and square the last one. Notice we did not get simply 4x squared plus 25. However, I did get an equation without a radical in it. It's now a quadratic equation. To solve that, I need to set it equal to 0 and try to factor it. So big fat zeros over there. Minus 4x minus 5 gives me 4x squared minus 24x plus 20 equals 0. And I notice that these all have a factor of 4, so I can either factor that 4 out, but since 4 is not the one that's 0, and I have an equation, I can also divide that 4 out, and then I don't have to be concerned with it, and it makes my numbers smaller and easier to factor. X squared minus 6x plus 5 equals 0. Meaning this is x minus 5, x minus 1, two numbers that multiply to give positive 5, but when I add them, I get -6. So either x is 5 or x is 1. But don't forget, I must check those answers in my original equation. So let's start with the 5. So the square root of 4 times 5 is 20 plus 5 minus 6. Is that 2 times 5, 10, excuse me, let me get a drink right quick. is that, let's see, is that true? The square root of 25 minus 6 equals -1. 5 minus 6 equals -1. Yes, it does. So I know that at least 5 is a solution. Let's try 1. So the square root of 4 times 1, 4 plus 5 minus 6, does that equal 2 times 1 minus 11? Well, that would be the square root of 9 minus 6. Is that equal to -9? Is 3 minus 6 equal to -9? No, it is not. Be sure you don't leave that. You must tell the problem that's not possible. Okay, let's look at one that has 2 radicals. Remember, the only way your radical is going away is if it's isolated all by itself. One radical on one side. So you cannot get rid of both these radicals at the same time. You cannot square individual sides. Individual terms. You must square both sides, right? So if I were to square this side, I'd have to do my distributive property to multiply that out. They will not both go away at the same time. So I'm going to isolate one at a time. The other one will not go away. Okay, so that's a big fat 0 now. And I have the square root of 4x plus 1 equals 2 plus the square root of x minus 1. Now that one of the radicals is isolated, either one, doesn't matter which one, I'm going to square both sides, not individual terms. So a square and a square root undo each other to just leave 4x plus 1 on this side. But here is another beneficial use of knowing that shortcut. A lot of times people still aren't quite sure how to multiply that out when you're doing the square root of x minus 1 times the square root of x minus 1. But the shortcut tells me square the first term, multiply everything together, which would just mean 2 times that, and double it, so 4 times that, and then square the last term. What happens when you square a square root? It cancels, right? It undoes itself. So that leaves just plus x minus 1. I still have a radical though. So I've got to do this process all over again. First step is isolate it. It has to be all by itself. So I'm going to move the 4 so that that's 0. I'm going to move the x so that that's 0. I'm going to move the 1 so that I wind up with 3x. 2 minus 4 is -2 equals, all of these are zeros now. The only thing left over here is 4 times the square root of x minus 1. Now, this radical is isolated. This term, this is one term hooked together by multiplication. Remember, terms are separated by plus and minus signs. I have to have this term isolated. If these numbers were divisible by 4, I would divide by that 4, make my number smaller. If I do that here, while I can do that, if I do that, it's going to make fractions over here, 3/4 and 1/2. And I know I'm about to square this. I do not want to involve fractions, so I'm leaving the 4 over here. Again, if this were a 16 and an 8, I'd divide everything by 4, make my number smaller. But I don't want to make fractions. So once I get my radical term isolated, I square both sides. Not individual terms, both sides. Multiplying this out means you square the first term. You multiply everything together, negative 6x, and double it, and then square the last term. Okay, now because this is multiplication, it does mean I just square each one. When you square a square root, they undo each other. I got rid of all my radicals. I notice it's a quadratic equation now, so I'm going to distribute this, set it equal to 0, and try to factor it. So 9x squared minus 12x plus 4 equals 16x minus 16, setting it equal to 0. I get 9x squared minus 28x plus 20 equals 0. And I'm going to try to factor. Well, let's see, two numbers that multiply together and equal 180 and add to give negative 28. Well, 180 is 18 times 10, so there's my numbers. If we use our shortcut, they both got to be negative, right? If we use our shortcut, I can just put those numbers in my factors. If I remember to go back and divide by 9 to simplify that. If you don't know what I'm talking about here, we can talk about that during class time. So this leaves x minus 2 times 9x minus 10 equals 0. So either x is 2 or x is 10/9. Don't forget I have to check these answers. So let's start with the 2 in the original equation. Square root of 8 plus 1 minus the square root of 2 minus 1, is that equal to 2? Is the square root of 9 minus the square root of 1 equal to 2? Is 3 minus 1 equal to 2? Yes. So that one works. Let's try 10/9 in the original equation. Is the square root, now if I put 10/9 here, that's 40/9 plus 1. I know I'm going to need a common denominator. Let's go ahead and make that 1 9/9 minus the square root of 10/9. Again, a common denominator. I can write 1 as 9/9. Is that equal to 2? So is the square root of 49/9 minus the square root of 1/9 equal to 2? Is 7/3 minus 1/3 equal to 2? 6/3 equal to 2? Yes. Notice this time they were both solutions. I must check both answers every time. Okay, we can even have higher powered radicals. We just simply, instead of squaring both sides, cube both sides. The radicals are already isolated, so I cube both sides, and a cube root will undo each other, leaving simply 2x equals 5x plus 2. A linear equation, an easy linear equation to solve, giving negative 3x equals 0 plus 2, or 2. Divide by negative 3. So x equals negative 2/3. Because I had an odd root, an odd index, I don't have to check that answer. Remember, with odd indices, that we can take the cube root of -8, right? I don't have a problem with negatives being under our odd radicals. And in addition to that, my answer would be negative. So I don't have the issue there with the negatives and positives that I do with even roots. I must check my answers on even roots, not odd. Okay, same thing for this one. Realizing that fractional exponents are radicals, think about this. I can write that 4x to the 1/5, and hopefully we should know this, is the same thing as 4x to the 5th root. So these fractional exponents really mean radicals. I can change this problem to x minus 3 squared, the 5th root of x minus 3 squared, and the 5th root of 4x. Meaning, then I can just raise everything to the 5th power to get rid of that index. Again, it's an odd index. I'm not going to have to check my answer when I'm finished. I can if I want to, but I don't have to, right? So I'm going to raise everything to the 5th power, because that will undo a 5th root, and simply leave x minus 3 squared equals 4x. And I've got a quadratic equation. I can't use my square root method, even though it looks like it's set up perfectly, but it's not only numbers on the other side, right? So I've got to multiply this all out. X squared minus 6x plus 9 equals 4x, and then try to go from there. So I'm going to try to factor it. Needs to be set equal to 0. X squared minus 10x plus 9 equals 0. Means x minus 9 times x minus 1 equals 0. So either x is 9 or x is 1, and because it's an odd index, an odd root, I don't have to check my answer. All right, so we really wouldn't have to rewrite that problem either. I just need to recognize that, wait, fractional exponents are radicals. Fractional exponents are radicals. Fractional exponents are radicals. So I could have just said, let's just raise this to the 5th power. Raise this to the 5th power. Right? Because when I have an exponent raised to an exponent, I multiply. 2/5 times 5. Notice what happens. 2/5 times 5. Right? So that'll cancel, leaving the x minus 3 squared, and the same thing here, leaving just the 4x. Okay. The exception to those higher powered roots is if you cannot isolate both radicals at the same time. In other words, if there's an extra term. Notice on this, if I tried to move my this middle term over, I'd have this minus 3. And remember, I can't go through and cube individual terms. I'd have to cube both sides, which cubing both sides would be a massive undertaking, right? I'd have all this distribution to do, etc., etc. So instead, we have some problems that are called quadratic in form. To be quadratic in form, there's 2 things you got to check. It has to have 3 terms. It has to have 3 terms, which this one does. So make sure it has 3 terms, and then look at the exponents. If you can double the exponent in the middle, and it's what's sitting right there, like 2 1/3 is 2/3, then it's called quadratic in form. If it's called quadratic in form, we have a special way we can solve that. Okay, but make sure, first of all, that it is actually quadratic in form. Note that the generic form of a quadratic equation looks like this. Now remember, with a quadratic equation, whether it factors or not, I can solve it. I can solve any quadratic equation. Notice that it has 3 terms. And if I double this exponent, 2 times 1, it's sitting right here. That's why this is quadratic in form. But this is crazy. I don't know how to factor that. This I know how to factor. Or plug into the quadratic formula, or whatever I need to do. So if I can make this look like a generic or a general quadratic equation, so the way we do that is we're going to use substitution. And usually we use a U for substitution just to remind us, hey, I'm not through with the problem. U, that's kind of a weird thing to have in our equation. Oh yeah, it means don't leave that U. And I'm just going to take this middle variable part, not the coefficient, only the variable part, and I'm going to say let that equal U. So this whole variable term, that automatically means that this first variable part equals U squared. Remember, I checked it to make sure 2 times this was sitting right there. So if I were to square this term, right, U squared, I would get, not this term, this term. If I were to square this term, I would get 2x minus 1 to the 2/3. So that's U squared. That's U squared. So every single time, I'm just going to let U equal the variable part. That'll automatically mean this is U squared. So the constants, right, and the coefficients are the only thing I'm pulling out of here. And then I'm going to replace the variables with U. So this would be 1 U squared plus 2 U minus 3 equals 0. Oh, that's a very easy quadratic equation to factor. 2 numbers that multiply to give -3 and add to give 2, +3 and -1. Meaning either U is -3 or U is 1. But don't forget, U, what does that mean? I'm trying to solve for X here. So don't forget, I've got to substitute back in, instead of U, U is 2x minus 1 to the 1/3 equals -3, and 2x minus 1 to the 1/3 equals 1. Okay, now these I can solve, right? This is just like what we were talking about. I'm going to raise both of these to the 3rd power. Which gives me 2x minus 1 equals -27. Now I can solve this equation. 2x equals -26. So x equals -13. It's an odd root, so I don't have to check it. But then I'm going to do the same thing to this one. Raise to the 3rd power, both sides, which means 1/3 times 3 is 1. It just leaves me 2x minus 1. 1 cubed is 1. So 2x equals 2, or x equals 1. Quadratic in form. And that'll work with any equation that can be deemed to be quadratic in form. And the two things that determine whether it's quadratic in form, it has to be 3 terms. And if I double this exponent or multiply it by 2, however you want to think about it, and it's sitting right there, then it's quadratic in form. So this one is quadratic in form. If that's the case, I'm just automatically every single time going to let u equal whatever the middle variable part is. The only thing I'm going to get out of this equation are the coefficients and the constant. The variables I'm substituting for. If this is u squared. Right? So this gives me the equation 7u squared minus 10u minus 8 equals 0. And I'm going to try to factor that. So I need two numbers that multiply to give negative 56 and add to give 10. Let's see. Let's go over here and see. Those don't come to me right away. So they've got to multiply and give negative 56 and add to give 10. So I know 7 times negative 8 are two possibilities, but that's not the number I need. However, it gets me started. I can change this 8 to 4 times 2. So now I have lots of combinations. There's 28 times 2, but that's not 10, right? Or there's 14 and 4. There it is. One of them needs to be negative. 14 times negative 4. 14 times 4. And 14 minus 4 is 10. Again, using our shortcut then, I have u plus 14 times u minus 4 equals 0. Got to divide by 7 to finally get u plus 2 and 7u minus 4 for my factors. That means u equals negative 2 or u equals 4/7. But once again, I don't care what u is. So what? I need to know what x is. So substitute back in. Oh, u is x to the negative 1. X to the negative 1 is negative 2. Or x to the negative 1 is 4/7. So I've got a couple of choices here. I don't care what x to the negative 1 is either, any more than I care what u is, right? I'm not finished until I have x equals a number. So I've got to get rid of this negative exponent. One thing I could do, just like with the fractional exponent, is raise that to a power that makes it positive. So let's raise it to the negative 1. Okay, negative 1 times negative 1 is positive 1, so I'll wind up with x. I still have to think about what it means to be a negative exponent, though. I can't leave an answer negative 2 to the negative 1. And remember, negative exponents have nothing to do with negative numbers. Negative exponents have nothing to do with negative numbers. Negative exponents mean reciprocals. Oh, so this is 1 over negative 2 to the positive 1. Right? 1 over negative 2 to the positive 1. It's not a radical, so I don't have to worry about whether I need to check my answer or not. These are not radicals any longer. Fractional exponents are radicals. These are reciprocals. So once I realize that the negative exponent means a reciprocal, I could just say, oh, then if x to the negative 1 is 4/7, x to the positive 1 must be 7/4. Okay, the last kind of problems in this section, finally, right, are work rate problems. Work rate problems are applications that are very easy once someone kind of shows you the method. It may be something that you never come up with on your own, but once you're shown, what happened to my arrow? Oh no. Once you're shown